I don't consider a lot of this stuff difficult. I consider it just lack of attention to the details that are presented to you and asked of you. Okay, guys. Aromatics. Any questions about aromatics as I get things together here? I gave you a purple today. Reactions of aromatics will begin on Friday. Let's try to finish up aromaticity. By the way, nomenclature, I posted a video several days ago. Okay, that's in the white handout. I went over that in the video. Have I watched the video yet? TNT? Hmm?
I started it, but I didn't finish it. So I don't know.
TNT. It's dynamite. Okay, let's see what we have here. Key to drawing MO diagrams. Was there another handout? Green one? Okay. Two additional things to be looking at. Aromaticity of ions, cations and anions. Can they be aromatic? Yes, they can be. We'll look at that now, and then we'll look at heterocycles. Compounds with heteroatoms. Non-carbon, most common being oxygen, nitrogen, and sulfur. Okay, top down here. Aromatic, anti-aromatic, or non-aromatic?
Anti or non-aromatic.
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 There's two H's here. sp3, no p orbital. That carbon's sp3, no p orbital. Is this a cyclic conjugated system?
No.
No, then it's neither aromatic or anti-aromatic. We just call this non-aromatic. This is no more aromatic than water or butane or ethanol. Okay? Non-aromatic, no p orbital. On the other hand, what if we are able to treat this with some type of base maybe and remove an H+, okay? Maybe like hydroxide, we'll have to see if that's strong enough base. Take the H, leave the electrons behind as a lone pair, and make the Carb Anion. Can this be done? Well, we can always show an acid-base reaction, but then we have to say, can this actually be done? And we have to judge pKa's, etc. But this would be an acid-base reaction. Now, it's just hydrocarbon. It shouldn't be that acidic. What about the anion over here? Aromatic, anti, or not? Well, it's one of the answers, and we can assess this the same exact way. Is this a cyclic conjugated system?
Yeah.
P orbital. There's your pi bond. One electron make pi bond. One electron make pi bond. What's the hybridization of this carbon here? And what type of orbital is the lone pair in?
sp2
Can we again, Alex?
sp2
sp2, and the lone pair is in a
p orbital.
Exactly. I stressed this back in August in Organic 1, very beginning. And I said, anytime a lone pair is next to a p orbital, the lone pair is going to want to be in a p orbital. Yes? Next to a p orbital. This lone pair is in a p orbital. One electron make pi bond, one electron make pi bond. How many p orbitals here?
5.
5. Number of pi electrons, that is electrons in the p orbitals. 6. That's the most important there. You got a cyclic conjugated system with 6 pi electrons. That is the definition of what? Aromatic. 6 is a 4n plus 2 number. Okay? cyclic conjugated system with 6 pi electrons, 4n plus 2 number. It's an aromatic anion. This anion is quite stable, much more stable than a regular carb anion. pKa of this, is it written down somewhere? It might be down lower.
16.
Yeah, I thought about 16. That sounds a little low, so I was questioning that. I was thinking maybe it's 20. 16 is pretty low for a hydrocarbon. A CH that's fairly acidic for a CH, just a hydrocarbon. Why is it so acidic? Why is it so readily or eager or willing to give up an H and become a minus?
Because it becomes a conjugated system.
Because the anion is aromatic. It doesn't take much effort to get there. It's willing to do that. It's relative, okay? Where if you take just a regular hydrocarbon like cyclopentane, pKa is going to be greater than 40. I mean, making this anion, there's nothing there. It's just sp3. So we can explain the relative acidity of this hydrocarbon here. The anion is aromatic. What about this anion over here? Carb anion. Anybody know what carbon anion? Carb anion, that's what we're looking at. Carb anions. Is this a cyclic conjugated system?
Yes.
We can put this in a p orbital. P orbital here, 1, 2, 3, 4, 5, 6, 7. 7 p orbitals. Number of pi electrons. Number of pi electrons? 8. What do we have here? Is it cyclic conjugated?
Yes.
It appears to be.
It's anti-aromatic.
It's certainly not aromatic. If this is cyclic conjugated, it's anti-aromatic. Anti-aromatic. But importantly, if planar, that is, if it is indeed fully conjugated. Do you think it wants to be conjugated? No, it would like to be able to buckle or something and disrupt that conjugation. The conjugation leads to actually bad. Not all conjugation is good. Organic one, we said conjugation is always good. I probably said that. That's actually a case, anti-aromaticity is a case where conjugation is actually bad. Because it allows the electrons to interact in some bad ways. I don't know if it is indeed anti-aromatic. Again, a lot of compounds do something to avoid it. So a lot of times you say, well, if planar, it would be anti-aromatic. It's certainly not aromatic. So that anion is much less stable than this one. That neutral compound is much less acidic. That neutral compound does not want to become that anion. This one, however, does. Aromatic anions. Let's try the cations. How about the first compound? It's not a cyclic conjugated system. We have an sp3 carbon, no p orbital. Game over. Nope, not a cyclic conjugated system. All right? Non-aromatic. Well, how about the cation? Now, cation, this is not going to be formed by an acid-base reaction. It would have to be formed by some other mechanism. We can show that a little bit later. Let's just consider the cation. Well, what's the hybridization of a carbocation?
SP2.
sp2. It has 3 bonds. 2 to carbon. There's 1 undrawn hydrogen there. It's good old-fashioned sp2. sp2 has a p orbital. What's in the p orbital?
0 electrons.
It's empty. Empty p orbital. And that's why it reacts. Nucleophiles come in here and add to that empty orbital. But then we have, how many p orbitals do we have here? 7. That's really isn't our main thing we need to be looking at. The main thing is number of pi electrons in the system. How many?
6.
6. What do we have here? Cyclic conjugated system.
It's air.
P orbital on every atom. 6 pi electrons in the system. Because once it's fully conjugated, it becomes one system. And how many electrons are in that system?
6.
6. Aromatic. 4 and plus 2 number.
If
Aromatic cation. Or carbocation, right? So here the 7-membered ring. These are 7-membered rings. Okay? Let's see, I want to memorize this, right? The 7 cation is aromatic, but the 7 anion is anti. Let's just memorize that, right? No, don't do that. Understand how to assess. Question?
you always want to, even though if it's like could be aromatic or anti, you always want to put if planar in our answer, or
Yeah, every one of these, even that assumes it's got to be planar. Because if for some reason it could not achieve planar, now this one would want to be planar. I mean, because things want to be aromatic. Things want to be lowest energy as possible. I don't know of any or see anything why it wouldn't be, but again, I don't know all the answers. You have to collect data on your compound to see if it's exhibiting this aromatic property. Theoretically, I expect it is, yes. We're doing theoretical expectations. If planar would always be good to know. What about the 5-member ring over here?
anti-aromatic.
This one's anti-aromatic. You see that? How many pi electrons in that system?
4.
4. One carbon has no pi electron, empty p orbital. Yes, assuming it's planar. Then we can ask questions like this. Which one of these cations do you think is easiest to form? Kind of duh. The aromatic one. All right. So now we're able to predict things like that, which is easiest to form. The one on the right over there is certainly not aromatic. It'll be very difficult to form this. But hold on, isn't it resonance stabilized? Can't we do resonance structures? Yeah.
That's right, it's anti.
I thought resonance stabilized cation. Traditionally, it typically does. But the resonance here, by the way, let's do resonance structures here. Remember the old windshield wiper? Let's see, we get boom, boom, cation there. How many additional resonance structures do you think we're going to be able to draw here? This being one additional, how many total additional?
All the same.
4 additional, that being number 5.
But they're all the same.
They are all the same.
It's going to have the same.
Let's do them. Okay. We can move these up here. Resonance arrow. Double-headed resonance arrow. By the way, some of you new to me on mechanism questions, WDAM, if you get that on your test. What does arrow mean? It means I do not know what your arrow means. Either you used your arrow incorrectly, or you used it correctly, but then you showed something that didn't come from your arrow movement. Mechanisms are largely, part of it is you being able to use arrows correctly, mechanism arrows. That's going to give my bond here and here plus there. And we can windshield wiper these over. Boom, boom, plus there, yeah. Now we can windshield wiper these down like that. Boom, boom, plus here, yeah. Standard old electron movement, resonance structures. And now if I move these up, plus here will get us back here. 5 total. The plus charge falls on every carbon here. Yes. Which resonance structure is major?
All of them are the same, so it's kind of the same amount of instability.
Right, they're all the same. They're all equal contributors. What does the hybrid look like? The hybrid is bond and a half all the way around. Maybe not exactly bond, well, it should be exactly bond and a half. It doesn't. I mean, single bond, single bond, single bond, double, double. But there's a charge here. What I'm getting at is the last structure I drew here, just the charge that's sort of delocalized. Sometimes you may see this drawn like that. It's sort of a hybrid look. Same thing for the anion above up there in the middle. You can do the same thing with resonance structures, and you can sort of just show it like that. There's a lone pair here. Okay? Understand the hybrids here in terms of a classical resonance structure view. Fully delocalized cation, assuming it's planar. Because if it ain't planar, all this is all. No MO, no resonance, it's all just isolated. Problem is, that cation there is pretty unstable. Even though we just did a lot of resonance, and that's because resonance here is bad. Because we've got a cycloconjugated system with only 4 pi electrons, and that's bad because the MO theory takes over and is actually a diradical because of that. Unusual acidity, we've already looked at that, okay? Already looked at that. This one, though, these seem very similar, right? I mean, it's going to be a conjugated anion. We've already looked at that, although the one I drew over here was not, you have any pi bonds in it. But if you're talking about this being an acid, you're going to make an anion here. Well, that anion is not going to be that favorable. That anion would be anti-aromatic. So that compound is not going to be as eager to act as an acid. That's forming anions. Forming cations, though, how can we make a cation? Well, just think mechanistically. I mean, can you get a carbocation here? Yeah, we can protonate this, yeah. And then if this leaves, right? What are we going to make here?
A stable aromatic
carbocation. But what, is it going to have any stability?
Mhm.
Right? Mechanistically, this is the mechanism for doing this reaction. Aromatic cation. This reaction, and forming the carbocation is typically a rate-determining step. This reaction is very easy, very fast, because it's so easy to form this aromatic cation. On the other hand, the reaction on the right is very difficult and almost impossible. It looks like they'd be the same. But over here, what are we forming here?
Anti-aromatic carbocation intermediate.
Anti-aromatic carbocation. Not going to be easy to form. Reaction is not going to want to proceed. Consequences of aromaticity or anti-aromaticity. Does this make sense? By the way, those were monocations, monoanions. You could also have dications. And there's a question or two in the workbook. You'll probably also find in your textbook. Dications. But you ask the same types of questions when you assess these. The most important question is number of electrons in the cyclic conjugated system. Assuming if it is indeed cyclic conjugated. Okay, heterocyclic compounds. Compounds that contain something other than carbon, like nitrogen. Ah, the world of heterocyclic chemistry. This is good chemistry. Okay, lots of heterocycles. All right. Heterocyclic chemistry is a major branch of organic chemistry. All right. You've seen amino acids. You have to learn amino acids.
Yeah.
Okay. Histidine has an aromatic or a heterocyclic ring in the side chain. Okay. Lots of drugs contain heterocycles. Pyridine, we've used pyridine before as a weak base, or it's borderline weak. Sometimes we actually it's called it strong, but it's very borderline. Okay? We need to understand structure, we need to know the name. It's basically benzene, where one of the carbons is replaced for nitrogen, or CH is replaced for nitrogen. There's no H here. There's a lone pair there instead. All right. Hopefully you guys, I stress this for organic 1, questions like this. What type of orbital is this lone pair in?
SP localized. SPG localized.
SP3.
What type of orbital is the lone pair in?
S2, SP2.
No, it's not SP3.
SP2.
SP3 atom doesn't have a pi bond, doesn't have a p orbital. And you see that nitrogen making a pi bond. It's got to have a p orbital. The lone pair is in an SP2. SP2. If we graph this from organic 1, remember that? Nitrogen is SP2. It's got 3 hybrids and a p orbital. What type of bonds do you see the nitrogen making?
Sigma bond to carbon, pi
Sigma
bond
bond to carbon.
pi bond to carbon,
Sigma bond to carbon.
pi bond to carbon.
Pi bond to carbon.
Lone pair sits in the SP2.
And the lone pair is in SP2. The p orbital is being used to make the pi bond that we see. What about the aromaticity, though? Is it a cyclic conjugated system? Yes, every atom has a p orbital. Now, this has been shown here. I took this from a drawing somewhere. Here's the nitrogen over here. Nitrogen has a p orbital. So do all the other carbons, and you see the cyclic conjugated system of six p orbitals. The lone pair is sitting in a hybrid. And we know that the hybrids are perpendicular to the pi system. But you got, I don't know if these numbers are here, but it's 6 p orbitals, right? And 6 pi electrons. But right there, cyclic conjugated system with 6 pi electrons, it's aromatic. The most important thing here is understanding that the lone pair is not involved in the conjugation, not involved in the aromaticity. The lone pair is in a hybrid. Just ignore it. There's your aromatic compound, just like benzene. That's in a hybrid. What about basicity? Well, pyridine is basic. Because the lone pair is able to react. It's not delocalized. It's not conjugated. So pyridine is a good old classical aromatic compound. Question?
Sorry. Did you just say the lone pair is not contributing to the cyclic conjugated system? That's what you said?
Right, it's not.
Okay.
No, it's here. 2, 4, 6. Here's the nitrogen. 1 electron, make pi bond. 1 electron, make pi bond. 1 electron, make pi bond. There are your 3 pi bonds. 6 pi electrons. Now, 1 electron from the nitrogen is in the pi system. The arrows are my electrons for nitrogen. Right here. 1 electron's in the pi system. P orbitals. The lone pair is not in the pi system. The lone pair is in a hybrid. The sigma framework. That's a pyridine type nitrogen. Here we have a compound known as pyrrole. What type of orbital is this lone pair in?
P orbital.
That's in a p orbital. If we graph that from organic 1, it's sp2. Why is it sp2? Because at the beginning of organic 1, you should have thought it was sp3. But then we clearly got past that because we said anytime a lone pair is next to a p orbital, we're going to want to be in a p orbital. What about up there? Anytime a lone pair is next to a p orbital, it doesn't work up there because the p orbital next door is already interacting with something, making the pi bond. What type of bonds do you see? Sigma bond to carbon, sigma bond to carbon, sigma bond to H, and the lone pair is in p orbital. And if you show all 5 p orbitals conjugated, 1 electron make pi bond, 1 electron make pi bond. And in the nitrogen, we're going to put the lone pair. And we have a cyclic conjugated system with 6 pi electrons. It's aromatic. Now in the sigma framework, the nitrogen is making a sigma bond to the H. Pyridine and pyrrole are both aromatic. A huge difference though, pyrrole is not basic. Because here, the lone pair is conjugated, it's delocalized, it's involved in the aromaticity. However you want to say that. It's busy. you can actually draw resonance structures using the lone pair. Now, there are some degrees of aromaticity. A lot of your heterocycles are not fully, ultimately, optimally aromatic, because they're not optically delocalized. And so, while for our class we'll say yes or no, aromatic or not, there's actually a continuum of how aromatic it is, but we're not going to get into it in this class. How delocalized is it? The problem with some of these is when you start doing resonance structures, right, like that, that's minus and this is plus. Good old classical resonance structure. Net neutral. But these resonance structures are not equal contributors. Which one's better, right or left? Left. And so it prefers to stay one, it has some isolated characteristics. See, benzene is the granddaddy of aromatics because it's so delocalized. Because all resonance structures are equal and it's just fully delocalized, optimal aromaticity. For this to be fully delocalized, the nitrogen has to just let its lone pair just go completely delocalized. And it may not want to do that much because it becomes positive charged. Here's some drugs. Histidine. This is just an extra nitrogen. This is called an imidazole ring. Here's imidazole. It's found in histidine. What about it? Aromatic? Whatnot? Lone pair here, lone pair here. This is just combining the two different types of nitrogens into one compound. Imidazole is also found in Versed, benzodiazepine type sedative compound. How many aromatic compounds, or how many aromatic rings in Versed? And then we'll finish up here. Please look at these three, and we'll answer these quickly next time. Assess these. What do we have down here?
Heterocycles.
And maybe draw hybridization diagram. You know, you guys that didn't have me didn't do that organic one, I'm pretty sure. I think that's very useful. Organizing where everything is. Have a good day, guys. We'll finish that up quickly on Friday.